here's a different, the probability of a positive test given no disease present is 0.07. This is called the probability of a false positive. So that's all the information we have. Now we would like to answer the question, what's the probability of a disease being present given that the test is positive? Oh. Without some kind of a roadmap, this is not going to end happily. So let's do a tree and maybe hopefully we'll be able to populate the tree with enough numbers that. So first division is disease, no disease. So this is the disease step. And here we put the probabilities that we were given. And what's this one? 1 minus 0.008. Now we conduct the test. Positive, negative, positive, negative. We do know some of these numbers. The probability of a positive test, given that the disease is present, there is a sensitivity. That means that this one has got to be 1 minus 0.9. The probability of a positive test given no disease, 0.07. I want this conditional probability. If I follow the reasoning up here, what I'm after is the probability of disease given positive test. That's what I want, times probability of positive test equals probability of positive test and disease. And disease. So we should know 2 out of those 3 numbers. We'll be able to find them. What's the probability of positive and disease? What's the probability of positive? Then we can figure out the probability of disease given positive. So how do we get it? Well, positive and disease multiply 0.90 times 0.008 is 0.0072. See, we did exactly the same thing as we did up here. To get ace and ace, we took the probability of ace given ace in the first times the probability of ace in the first. To get positive and disease, we take the probability of positive given disease multiplied by the probability of disease. Okay. Uh-oh. Probability of positive.
We multiply the two positive if disease is present and if disease is not present.
So here, I don't know if it's simpler to think of the ACEs or just to think of this situation. The way you compute the probability of a positive test is add the probabilities associated with the branches that lead you to positive. So that would be this one, 0.0072, plus this one, 0.992 times 0.07. That's how you get the probability of a positive test overall. And that number is 0.0766. This is the number we want. So we divide 0.0072 by 0.0766 to get the number we want. Question mark equals 0.0072, 0.0766, and we get 0.09. So the probability of the disease being present given a positive test is 0.094. The chances of the disease being present is less than 1 in 10. So this is called the rare disease example. And in every class where you study conditional probability, and anytime you study probability, you study conditional probability, they trot out this example to give an indication of the importance of reasoning with conditional probabilities. Because if you were in the position of receiving the news that you have just tested positive for, you might be quite concerned. This seems to be giving you reason to be at least not suicidal at this point. Maybe another test is in order. Not convinced. These aren't unrealistic numbers in terms of sensitivity. In fact, these are quite accurate tests. As tests go. 20.4%. So, your assignment. You're free to think about this if you like. There's an assumption being made here that's very significant that's led to this conclusion. All of these values we can take to be correct as far as this toy example is concerned. The probability of a positive outcome given the presence of the disease is 90%. The probability of a positive outcome given no disease present is 7%. 0.8% of the population overall. So there's an assumption being made here behind this calculation may not be so clear. And I'll give you a couple of postings that discuss this issue. Okay. Here's the hint. This is the probability of the disease being present in the population. This probability and this probability are being computed with what population? Whole population? So maybe there's an issue. So, conditional probability, I thought about this a bit before I presented it to you. This can be really a confusing topic because the language gets mixed up with the math concepts, and you have to go back to the definitions of the math concepts, which we haven't spent much time on today, for this all to make sense. But I haven't lied to you about any of the mathematical derivation here. These calculations are all okay. It's just that there's an assumption here about these conditional probabilities and the populations involved. It's very important. Okay, so questions? How do you like Emory so far? You been here since Saturday or Friday?
So they've gotten to spend one day by themselves yesterday in the tower. Apparently, maybe didn't make it MARTA the way they wanted to, but they'll try that again. So, so far so good.
Which tower?
Claremont,
The new one?
well, no, it's an older building now.
The one that was, used to be graduate students?
Graduate students, yeah.
Has it been refurbished since then?
No, not really. No.
Okay. If you have any questions about placement or math classes to take or not, be happy to answer them. If you just want to stay and ask. Okay. If you feel like leaving, where's there to go now?
Back upstairs, W501.